All right. All right. John, are you there?
I am.
All right.
Good to see you. There's your disembodied head
I'm
again.
kind of fading in and out there.
Yeah, that's right. You're phasing out.
Yeah. So
All
so
right. I wanna just check our feed
Skrell
here real
power
quick.
cells, man.
Yeah,
Yeah, I know.
give me a quick sec, guys. I just want to check to make sure our feed on Facebook is working and on YouTube and all those good things.
I can
All
see
right.
us on Facebook.
Yeah, I see us on YouTube. Okay. Well, good evening, everyone. I'm Rich Ozer. I'm here with Gerald McKeegan and John Curry, and we got a break in the weather. And surprisingly, we're actually at the telescope tonight, or at least Gerald and I are. I'm not quite sure what planet John is on there.
I'm back in the lab.
You're back in the lab, right? But we did get a break in the weather. I know it looks like I'm probably dressed for snow, but it's not even that cold up here. So we
Yeah,
lucked
yeah,
out.
really.
So it gives us a great opportunity to have a live program tonight. Before we get started, though, Gerald, you want to give our visitors a little information about Chabot and membership and that type of thing?
Yeah. So Chabot is closed right now. Chabot Space and Science Center would normally be open to the public every week, and we'd invite people to come in and look at our exhibits and attend some of our programs. But unfortunately, because of COVID, we're not able to do that. So we are relying heavily right now on support from donors like you, uh, helping us out with our virtual programming, the virtual telescope programming. We have virtual science programs during the week, a lot of different virtual activities that is going on right now. Plus, we're working on upgrading some of our exhibits and doing some other work in the facilities. So we still have staff on board, and we still need to have a source of regular income. So we do rely heavily right now on donations. So on the Facebook page, if you see a donate button there, uh, please help us out by clicking there, or you can go to the Chabot Space and Science Center website, chabotspace.org, and there'll be a donation button there. Also, if you want to become a Chabot member, go to the membership page on our website and join up. Um, we have a lot of sponsorships, and if you were watching our slides going prior to our start here, you saw something about Fremont Bank. Fremont Bank has generously helped to sponsor Chabot Space and Science Center, so we really appreciate that. And hopefully, if you know of any corporations, your employer or a corporation, or you know somebody who runs a corporation that's interested in helping some nonprofits out, uh, give them our name and please ask them to help us out. All right.
Before we get started, I'd like to mention that you and I are here at the 36-inch research telescope at Chabot, and fondly named Nellie. And Nellie is a Cassegrain telescope, excellent for photography, and also used for public outreach on weekends when the center is open to the public again.
Hey,
Uh,
Richard, can you
yeah,
tilt your camera
yeah,
so people can
I
see
think I
see
can.
the
There
telescope?
we go.
Yeah, there it is right behind you.
Yeah, just enough light to
Yeah,
get it in.
yeah.
It's
So
it's an
this
it, it's
is
it's a magnitude 10 object here in the observatory.
yeah.
So
So this telescope is our newest telescope. It is a reflecting telescope, so it uses mirrors instead of lenses. And it's also our only computer controlled telescopes. We have three telescopes up here, observatory telescopes. The other two are they're antiques. One of them was built in 1883. The other was built in 1915. So they're all manual telescopes. They still work. We still use them. But in 2003, we had a new telescope built, this 36-inch reflecting telescope, and it is a computer controlled telescope, so it's ideal for doing these virtual programs like tonight.
yeah. There is a little leftover business from last week. We did our program last week from our homes, and we were talking about a lot of different topics in astronomy. And one of the topics that we discussed was the Pleiades. And there was some debate during the program on the distance from Earth to the Pleiades and the width, so to speak, of the Pleiades, basically the distance from the two farthest stars in the Pleiades from one another. So the answer is the answer is
Vague.
vague.
We don't
Yeah,
know.
the
Yeah,
answer is 400 light years from Earth to the Pleiades, more or less. And there's some who say a little bit less, some who say a little bit more. And the distance across is somewhere between 35 and 45 light years.
hey, Richard, why don't you let me do a screen share here while we're talking
Oh,
about it?
sure.
We can look
Let me
at it.
turn that on for you. Hold on for a sec here. Share screen. There we go. Give it a shot.
All right. So here are the Pleiades. The Pleiades is an open star cluster. It's in the constellation Taurus, the Bull. And this is visible to the naked eye. So if you went outside right now and looked off in the direction of the constellation Taurus, you'd see a little sprinkling of stars all close together. And that is the Pleiades, also known as the Seven Sisters. And these are all stars that formed out of the same cloud of gas and dust. And most of the gas and dust is now dissipated, leaving behind a bunch of very young stars that are all drifting through space together. They orbit around our galaxy. As they orbit, because they're not all exactly the same distance from the center of the galaxy, there's slight differences in their orbital velocities. And because of that, over time, they slowly separate apart from each other. But these are all very young stars. And as Richard said, they're just under 400 light years away. It's very common for stars to form in star clusters like this. Our sun formed in a star cluster like this. And astronomers love these open star clusters because since they're all the stars in the cluster are roughly the same distance away, any differences that we see in the stars are intrinsic. So if you see two stars, one is bright and one is dim, it's not because the dim one is farther away, it's because the dim one is truly dimmer than the bright one. So that helps astronomers figure out the evolutionary process of stars, how they live, how they die. And so we like to study open star clusters like the Pleiades. All right.
Yeah, thank you.
Okay.
So, we
I
can
think
get
think
to it, I think, right?
speaking of stars forming in
Yeah.
clouds of gas and dust, we've been promising you for several weeks now that we were going to look at the Orion Nebula. So the Orion Nebula is part of the constellation Orion. If you're familiar with the constellation Orion, it has three stars that are all lined up. We call the belt of Orion. And below the belt, you'll see a fainter string of stars we call the sword of Orion. And in the center of the sword, you'll see what looks to the naked eye like kind of a fuzzy star. If you take a pair of binoculars and look at it, you'll see that there's some very bright stars clustered together. And you can see them in this image that Richard is showing right now. Up there in the upper right, you see some stars. And those stars are what we call the trapezium. And they don't look very bright right now, but in a couple of minutes here, we're going to show you just how spectacular this object is. Those stars are inside of a huge cloud of gas and dust about 1,300 light years away, and it's where new stars are forming. Just like the Pleiades we talked about a minute ago, they formed within a huge cloud of gas and dust. For the Pleiades, the cloud is mostly gone now. In this case, the cloud is still very much there, and there are still a lot of very young stars still forming within the cloud, still embedded within the cloud. But these four stars here, it looks kind of like three right now. You'll see in a minute that it's actually, there's four stars there. They are very hot, very young stars that formed out of that cloud, and they are emitting a lot of ultraviolet radiation. So, Richard, why don't we switch to like
Yeah.
maybe a 20-second or 30-second
Yeah,
exposure?
so before I take that image, I'm going to warn you that what you're going to see immediately is a test exposure that we took before we got started tonight. And I'll tell you, that came out really nice. It's actually pretty spectacular. And you can see how much color that we can get from this object. Usually astronomical objects through amateur telescopes are black and white. We don't usually get a lot of color, but with an aperture the size of Nellie's, a 30-second exposure gives us the full spectrum.
So this is a huge cloud of gas and dust. As you can see, even from this test image, the cloud extends well beyond the field of view of the camera on the telescope. It's a very large cloud, and it's very dense in some regions. The four trapezium stars, uh, like I say, they're extremely hot stars, very young. They're so hot that they're emitting a lot of radiation, which is actually pushing the cloud away from them. And so they've formed a little pocket within this cloud, and that's what we're going to look at here. There you go. And that pocket is surrounded by all this gas and dust, some of it actually in front of the pocket. So you see that little dark thing that looks like a thumb sticking out on the left there. That's a gas cloud that's a little bit in front. And then behind the trapezium, you see more gas there. And you see a lot of color there. Again, there's a lot of ultraviolet radiation being emitted by those bright stars. Ultraviolet radiation, when it hits the gas cloud, it ionizes the gas and causes the gas to glow. So a lot of the light that we see is glowing gas, and the color of the gas depends on the composition. If there's just mostly hydrogen, it's going to be kind of pink or reddish in color. If there's a little bit of oxygen in it, oxygen glows in a very bright kind of turquoise green color. Uh, and then not only is the cloud emitting light, but it's also reflecting light from those stars. So you're getting both reflected light and emitted light from this huge cloud out in space. This is a real easy object to find. You can even see it in binoculars, and even a very small telescope will show you a lot of detail. And it's like I say, it's easy to find because it's right in the middle of the sword of Orion. Now you see three stars lined up uh, down on the lower left there. Those are not the three stars in the belt of Orion. The entire field of view that we're looking at is very small. If you imagine holding a soda straw at arm's length and looking through it, we're looking at an area actually slightly smaller than what you would see looking through that soda straw. So we're actually quite a ways from the three belt stars. And those stars, the belt stars, are actually separated so much that we couldn't see all three of them in the same field of view with this telescope anyway. So,
Harold, we have a
yes.
question from Mark. Have any exoplanets been detected in the Orion Nebula, or maybe solar systems haven't had time to form yet? Well, they have had
Well,
time to form. I don't know about whether we've discovered any exoplanets there
yeah,
yet or not.
not that I'm aware of, but that doesn't mean it isn't true. I suspect that planets are forming. One of the things you can't see in this image is that there's literally hundreds of stars embedded within the cloud. And it's only when you zoom in on a very high resolution image that you see these little knots of gas. And those little knots, they look like just little, you know, globules. In fact, they're sometimes called box globules. Um, And those are actually stars, new stars, still within the cocoon of gas and dust from which they are forming. Yeah, you're probably not going to be able to see one. You don't think you
No, but I
quite
thought it
there.
would be fun to zoom in anyway.
Yeah. So this is good. You can actually see that there's four stars there. If you did a much longer exposure, you'd
Yeah.
see more of the gas cloud and more detail within the gas cloud. But then the trapezium, because those stars are so bright, they'd wash out the center part of the image. So you're always kind of trying to balance between, how much light you get from the trapezium versus how
Right.
much light you get from the rest of the cloud.
Yeah, for such a bright and large field of view nebula, it's actually a very challenging object to photograph properly for the very reason you just
Right,
described.
right.
You need to take images that are respecting the brightness of the trapezium, and then combine those with images that bring out the detail in the nebula,
Right.
and use star masks and other techniques to combine the two without the whole center of the image being blown out.
Or do narrow band
Or do
filters.
narrowband. That's
Yeah,
right.
yeah,
Yeah.
yeah.
What I find remarkable here is, just in this very quick snapshot with this DSLR camera, how many shades of red we get. We got this pink and deep red. It's really pretty remarkable. I
Yep,
was
yep.
really
Yeah.
quite surprised.
Yeah.
And we associate the red cloud, that's typically hydrogen clouds. In fact, all of these clouds are mostly hydrogen. Um, but if you get a little bit of oxygen mixed in, oxygen glows really bright with just a little bit of ultraviolet radiation. And it glows much brighter than the hydrogen does. So even though there's much less oxygen, because it glows so bright, it kind of dominates the color in some regions here. Right. So we've been promising the Orion Nebula, and we finally fulfilled our promise.
Yes.
Promise is kept. Right.
Okay.
Yeah. Yeah.
I'll answer an earlier question from Erica's husband. Wants to know if there will be a leap second inserted this year. And I did check on that, and there is none planned at this point. There was not one added at the end of December, and there's not one planned for the end of June at this time, but that could
Well,
still
that's
change.
too bad. I was looking forward to the extra sleep.
Right.
Yeah. And this, of course, has absolutely nothing to do with the Orion Nebula.
Doesn't have
Yeah,
anything to do with the
but
Orion Nebula,
yeah.
or not much to do with astronomy, except that we do use universal or coordinated universal time. So I guess that's important.
Yeah. So for those of you who don't know what the heck we're talking about, our system of time is based on how long it takes the Earth to orbit around the sun and how long it takes the Earth to rotate one full rotation relative to the sun. So one full rotation of the Earth relative to the sun, that's a day, and one complete orbit around the sun, that's a year. So we divide the day up into hours, minutes, and seconds, and we divide the year up into days and fractions of a day and so on. And every once in a while we have to adjust because the time it takes the Earth to orbit around the sun is not exactly 365 days. It's about 365 and almost a quarter day. And so every 4 years we have a leap year to catch up. And so you're all familiar with that. But what you're not familiar with is the fact that there are minor differences in the length of a day and the length of a year because of a lot of different forces that are going on, gravitational forces, perturbations because of other planets, and so forth. And because of that, periodically we have to reset the electronic clocks that we all rely on to match the actual conditions out in space. And so periodically we have to add a second to the clocks to get everything resynchronized. When you you listen to, a TV station or a radio station and they report the time, they're reporting what's called coordinated universal time, converted to whatever time zone it is. So, right now the time here on the West Coast is 21:20, 9:20 in the evening. Um, that's our local time. You add 8 hours to that. That's coordinated universal time. Coordinated time is based on an atomic clock, which clicks exactly 8,000 or 84,600 or 86. No, it's 86,400 seconds per day. But because the days are not always exactly the same length, we have to adjust periodically for the slight variation. And there will be more and more adjustments because our day is actually slowly getting longer, and our year is actually slowly getting longer. So,
Well, that explains 2020, right?
yeah, yeah, yeah.
It
So,
sure seems like
anyway,
it.
enough of
Yeah.
that.
Yeah.
You can do actually a whole class on time and the different ways of measuring time and why we make these adjustments and why it's a problem, especially for astronomers who count things based on a very distant date. Um, what is it, 242,000 days ago, something like that, is the Julian date that astronomers use. And
Yeah.
so it gets pretty complicated.
Yeah.
All
Okay.
right. All right.
Anyway, Robert,
We were going to talk about the. Oh, I'm sorry. Was there a question?
yeah, Robert mentioned that Betelgeuse. He
Ah,
was
perfect.
observing Betelgeuse earlier today and noticed that
It's faded again.
there's a slight dark part on the lower part of it. I think that's what he's saying. And yeah, that is very possible. Betelgeuse is going through a lot of things. He does also ask if it's likely to go supernova
It,
within the next within the next 100,000 years. Yes,
yeah,
more than
probably.
definitely is.
Yeah, maybe a little bit more than that, maybe a lot less. We're not sure exactly when it will go supernova. A year ago, Betelgeuse, we ought to point the
Yeah.
telescope.
Why don't we? Yeah. Why don't we
Yeah,
do that?
why don't we just do that before we yak about
Okay.
that? So,
It's close to where you are.
Yeah.
yeah. So I'm gonna go ahead and slew.
Yeah.
You want to go to live view?
Yep. I'm
All
there.
right. And here we go. And there it is. So that is the star Betelgeuse. Actually, people like to call it Beetlejuice, but the correct pronunciation is Betelgeuse.
Careful, don't say that three
Don't say it
times.
3 times.
I don't know if you can see the orangish color on Facebook or not, but
Yeah. It's. Let me
It's a
try
little hard to
adjusting.
see.
It may be washing out a little bit, and that's why it seemed to.
yeah, the name, by the way, means the house of the twins. And this star, whose name I shall not mention a third time, uh, it used to be considered part of the constellation Gemini. And of course, Gemini is the home of the twins of Gemini. And so this star was originally considered part of that constellation. And so it got the name the House of the Twins, which is in Arabic, it is, shall I say it? Betel Jews, and it's not the other name. So anyway, this star is huge. It is a supergiant star. It's about 720, between 720 and 725 light years away. And if you go out and research the star, you're going to find all kinds of numbers for the distance. Computing the distance to this star has been a major task for astronomers over the last 30 or 40 years. You'll see numbers as low as 350 and as high as 800 and some odd. I forget the number I saw earlier today. But last year, a group of astronomers got together and they combined data from several different sources, both visual observation and radio observation, and came up with a distance of about 720 light years, give or take a few. And that is now considered the accepted distance to the star. Betelgeuse is so big that trying to measure its distance using the normal parallax method doesn't work.
Oh, I was about to ask, and that
Yeah,
totally makes sense because it's
its diameter
yeah,
is so
yeah,
big.
so
It's
big.
it's actually its angle on the sky is greater than its parallax. So
Yeah, so it obscures the method that would normally be used to measure a star at that
right.
particular distance.
Now it's a big star. It has a lot of dark spots on it. This star is in the final phases of its life. The fusion process is at the core. It's run out of hydrogen at its core. It's now fusing heavier elements. There's helium being fused, oxygen, carbon, so forth, and it's a bit turbulent inside, and that creates a lot of dark spots and some unusual activity. In October of, I believe it was, yeah, October of 2019, astronomers began noticing that it was getting fainter. The star is quite bright. It's in the constellation Orion. It's his shoulder. And if you look at the Orion constellation with the naked eye, it's very easy to see. I believe it's either the brightest or second brightest star in Orion. And it has a distinct orangish yellow color to it. And what astronomers noticed back in late 2019 is that it was fading. And there was a lot of concern about that because we know that the star is eventually going to die in a supernova explosion. So when we started seeing it fade, one of the things we think happens prior to a supernova explosion is the star goes through a series of contractions and expansions. And so there was concern that maybe something like that was going on. Well, it turned out that all that turbulence inside actually caused the star to kind of burp. And I've got a, if you'll bear with me here for a second.
In the meantime, Gerald, Betelgeuse does have a period where it brightens and dims
Yeah, but that's a very long period.
quite
That's
routinely.
yeah,
Yeah,
that's
Yes,
a
yeah,
long period. Yeah,
it
yeah,
exactly.
is. Uh-huh.
yeah. So this
But
there
this
was
this this dimming was much dimmer than that
Yeah.
than what it normally does.
It was out of band from the normal variability of the star, and it
Yeah,
was much
way out.
more. Yeah,
Mhm.
it was much more intense a drop.
yeah. I got a couple of things I want to share with you if I can here. First of all, I told you how big it is, just to give you an idea of how big it is. I've got a little image. Uh,
Are you able to
says
do screen share?
no, it's not letting me do it.
Hold
So
on, let me fix that.
still,
Errol, make a co-host. Okay, you should be able to do it now.
all right. So here is a graphic showing you how big Betelgeuse is. So there's Betelgeuse on the right, and that little dot you see over here on the left is the sun depicted actually bigger than it would be. I had to get it big enough so you could see it.
See it, yeah.
So, so, so the diameter of Betelgeuse is nearly 1,000 times the diameter of the sun. It's a huge, huge star, and it's very turbulent inside. And what happened? Let's see if I can get it up here. Hang on. Get the other one up here. Come on, there we go. Can you see that?
No,
Oh, why
you have to
not?
stop sharing and then share the second image. Yep,
Who invented this thing anyway?
I know.
All right. Now can you see it?
Yep.
Okay. So this is a diagram, and what we think happened was that Betelgeuse burped. It had a very significant coronal mass ejection, which happened to blow out right in the direction of the Earth. So you see what's happening here. Here's this huge puff of gas and dust. And over here, you see how it looked from the perspective of the Earth. It was a big cloud of gas and dust that was actually blocking our view of Betelgeuse, and that caused it to dim. Now, eventually, that cloud of gas and dust dissipated, and fortunately, I think around February or so of 2020, Betelgeuse brightened again to its normal brightness. But this is what we think actually caused that. So these kinds of eruptions are not unusual for stars that are nearing the end of their lives. This will happen probably 3 or 4 times or more. Most of them will not happen such they point right straight at the Earth. So we can expect to see that happen. An event,
It was an interesting event, but a lot of people were hoping that it was going through its final
yeah,
throes, because
yeah,
Yeah.
everybody wants to see that supernova. But
right.
Yeah. There's been some questions about whether or not, if it did go supernova, would it affect us here on
No,
Earth?
no,
It would
no,
not.
no.
It's too far away,
However,
but it will be visible. It would be very visible even in the daytime. It would be so
right,
bright.
right,
and it wouldn't
right.
make the Betelgeusians very happy at all.
No, no.
Yeah. So
Might affect the dead.
So anyway, that was a pretty interesting event, and it just reminded us that Betelgeuse is out there, and it's sooner or later it's going to put on a show for us. So that'll be pretty cool. All
Thanks
right.
for that. Yeah, let me put the share back onto the telescope.
Yeah.
There we go.
So anyway, that's Betelgeuse. A couple of other things that are up there right now. Not sure if we're going to be able to see it or not. There's the Clown Face Nebula.
I want to give it a shot.
Yeah, sure.
Oh, here's a
Uh,
good question in the meantime.
okay.
Yep.
Since Betelgeuse is that big, is it possible? Is it? Does that mean that Sirius is even larger?
No,
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 as a matter of
no.
fact,
Actually, Sirius
That's
is
a
about
great question.
it
That's
is a
right.
yeah,
good question though.
Yeah.
Yeah.
yeah. Sirius is about twice the diameter of the Earth. Sirius is
No, the
much.
sun. You mean?
The sun.
I mean the sun. Yes, thank
Yeah.
you. Yeah,
But
but
it's much closer than
much closer.
Betelgeuse.
Yeah,
Yeah.
Betelgeuse is 720 light years away. Sirius is a little over 8 light years away. So Sirius
Yep.
is much closer. We ought to look at Sirius tonight too, because that's a multiple star system, and there is one
Yeah.
other multiple star system I want to look at too.
Let's go for it.
Um,
Yeah. Good.
if I
Okay.
can
So next
find
is clown face, right?
right, all I gotta do
Okay.
is find it.
Got it. Yeah,
And
those clowns.
I'm not sure which name. So we have different ways of telling the telescope where we want to look. Yep, there it is. We can go to a star chart that's on the screen here, on the computer screen, and click on an object, or we can look up in a catalog that's in the same software. It has a catalog of a lot of well known objects, and we can just pick one from that catalog, or we can enter the coordinates of the object and tell the telescope to just go to those coordinates.
And while it's acquiring an image,
Here's
we
a
get to
here's a.
look at the Orion Nebula still from our previous
Yeah.
images.
And while we're doing that, another good
Yeah.
question: if Betelgeuse is so many light years away, how do we know that it hasn't already gone supernova? We
We
don't.
don't.
We don't know
Oh,
that.
It could have
Yeah.
happened.
We'll just find out someday.
Right.
yep. In the year 1054, people on Earth started noticing a bright star that appeared out of
There, that's
nowhere.
nice.
Um, yeah, that's actually a pretty good image.
Yep.
I'm going to slow down a little bit here. In 1054, people noticed a bright star that they hadn't seen before um, near the constellation Taurus, and it was so bright they could see it in the daytime. And it turns out that was a star that had gone supernova, and it put out enough light that they could actually see it in the daytime. That was in the year 1054. Today, we see where that star was. There is a huge cloud of gas and dust that is the remnant of that supernova explosion. It's called M1 or the Crab Nebula. So the object we're looking at here, we call the Clown Face Nebula. It is what's known as a planetary nebula. And a planetary nebula has nothing to do with planets. It's actually the remnant of a dying star. Now, this is a star that did not explode in the supernova. Actually, very few stars explode in supernovas. Most of them die via this process that you see here. These stars are lower in mass, similar to what our sun is. And when the star gets old, it swells up, becomes a giant star. As a giant star, it begins to blow off the outer layers of gas of the star in a process that takes tens of thousands of years. And over time, it loses a considerable amount of its mass. It can easily lose half its mass or more. And then the star runs out of fuel at its core and it collapses and becomes what's called a white dwarf. The white dwarf is surrounded by all of that gas that it expelled while it was a red giant. And the white dwarf is extremely hot. It takes all the heat energy that was left over in the star and compresses it down into a ball about the size of the Earth. And so there's a lot of heat being generated, and there's so much energy that it actually emits a lot of energy as ultraviolet radiation, which goes out and hits that cloud of gas that surrounds the white dwarf and causes it to glow. So what you see is glowing gas that was shed by this star when it was a red giant, and at the center is a white dwarf. Now, in this image, you see a bright red patch at the center. That's not the white dwarf. That's actually just very dense gas that's kind of saturating the image here a little bit. The white dwarf is a tiny dot right at the center of that big white spot that you see in the middle of the image.
Yeah. That would be hard to bring out, I think, under these circumstances.
Well,
Yeah.
fortunately, our friends at the Hubble Space Telescope,
Ah, yes. Those guys
uh,
have all the fun.
His
yeah,
clown nose is too big.
Yeah.
yeah.
Yeah. Go ahead and share that.
I think I have it somewhere. Maybe, maybe not. Oh yeah, they go by the other name.
Oh,
The
the
name that
obsolete
the name
name.
that shall not be spoken.
Yeah,
Yeah.
yeah. Astronomy has recently decided to get politically correct with some of the names that
Oh,
they
that's
use.
really beautiful.
So this is the image
Yeah,
of the
look
same
at that.
object taken by the Hubble Space Telescope. And what you saw is a big bright blob in the center. That's this whole part that you see right here. And the white dwarf is this little dot right there. That's the white dwarf. And it's surrounded by all this gas that was expelled in several episodes over a period of probably 100,000 years from the star when it was still a red giant.
I'd like to point out we had mentioned earlier the concept of taking images in narrow band. which basically means putting a series of filters in front of the camera that allow only certain bandwidths of light to pass to the sensor on the camera. And this is a narrowband image. This is why we get such fabulous detail, especially in the center of the image. And the colors, you'll notice, are really different than the colors that we saw in the camera hooked up to Nellie. And part of that is that, as the images come in, they can really assign any color they want to any of these frequencies of light that they're capturing. And there is a standard color palette for the Hubble called the Hubble palette. And when they take images of hydrogen alpha or oxygen 3 or sulfur, then they assign certain standard colors to it. So as you look at one planetary nebula next to another planetary nebula, both taken by the Hubble Space Telescope, you're able to see similar colors for similar types of gases.
And I'm going to stop share. And Richard, if you want to go back to your image
Yeah,
there,
actually, I wanted to show.
Dan Quigley
Yeah,
was asking whether our images are actually live from the
yeah, that
telescope.
that one is alive. Well,
Uh,
it's a 20-second image that we took a few
yes,
minutes ago. So
yes,
it's
but
as close to live as we can do.
yeah, the camera is on our telescope here at Chabot, so this object is actually pretty faint, so we need to do a 20-second exposure rather than a true live view. But it is live within a couple of minutes ago.
There,
So,
there is something I would like to show since we're talking about planetary nebula. Give me a sec here,
okay.
and I'm gonna share my screen to something else here. Bear with me. Here we go. So this was in the news this week. This is another planetary nebula called the Stingray Nebula.
Oh yeah.
It's very, very faint, and it is considered to be the most recent planetary nebula that has formed that we know about. So it's a very young planetary nebula. And, one of the things about deep sky objects is you really don't expect them to change dramatically year after year. When we're looking at galaxies or we're looking at nebula, we're looking at clusters, they look the same more or less year after year, unless there's like a special event like a supernova or a nova. And even decades or even 100 years later or 200 years later, they pretty much look the same. And that's why a lot of astronomers get interested in shallow sky astronomy, looking at planets, looking at asteroids, looking at the sun, because everything changes from day to day. But here's an example of a very, very dramatic change over just a 20-year period. And at first, it looks like, well, the gas has dissipated, but that's not what's happened at all. If you focus on the central star in the image on the left and compare it to the central star on the image of the right, you'll notice that the central star has dimmed considerably. So there's less ionizing radiation coming off of the star, and that means there's going to be less glowing of the surrounding gas because there's not as much energy to heat that gas up and make it glow in its various colors. And this is just over a 20-year period. So maybe in another 20 years, it's going to be barely visible at all. So I thought that would be a good
Yeah.
example of how the ionizing radiation from the central star plays a really important role in the visibility of the planetary nebula.
That's
Well,
very interesting, Richard. Are these two photographs um, basically the same magnification?
Yeah, they're absolutely identical to one another in terms of the configuration of the telescope, camera, and exposure.
yeah.
Very cool.
Yeah. Yeah. One of the things, if you look carefully at this, you can see that the gas that's been emitted is kind of in a almost like a tube type pattern. Um, and there's a torus or a ring around the probably around the equator of the star, and then there's gas coming off towards the poles in one direction, towards the other, fanning out, kind of like almost like an hourglass shape, but it's at an angle to us.
Hmm.
And you imagine
Yeah.
if what would happen if we turned this whole thing so that we were looking straight down the tube of the hourglass. This thing would look completely different. And one of the things we see with planetary nebulae is that they often have somewhat symmetrical patterns to them, and the pattern depends on what angle we're viewing the nebula.
Hmm.
Um,
That's why they all look different.
yeah, yeah. But they all seem to have some sort of symmetrical pattern to them, and it's a matter of what angle we're viewing it from, how it appears to us. All right.
To answer, Dan asked a question. Looks like the surrounding shell of gas has actually changed shape. I think that is an illusion, Dan, and because if you look really closely, you don't have as good a view on Facebook as I do on the much larger screen in front of me. You could see all of the features of the version on the right-hand side in the version on the left-hand side. It's just that surrounding features have become invisible because of the decrease in ionizing radiation. All right, I'm going to stop my share
All right.
and we're going to go back to the telescope.
Yeah. I was thinking we'd go to Castor,
Okay,
the, the
Okay.
multiple star system.
that's a great idea.
So I'm going to go ahead and set this to slew. But before I do that, I'm going to share my screen here for a second.
Okay,
And yeah, maybe not. Hang on.
you having problems?
No, I just didn't get the image up yet.
Oh,
I thought I did. Yeah, there it is. All right, we'll try it one more time. There it is. Okay, so this is the constellation Gemini, as you would see it in a star chart. Gemini is sometimes called the twins. There are two stars in Gemini, Castor and Pollux, that are, to the naked eye, they look almost the same brightness. In reality, Pollux is brighter, but Castor is a very interesting star. To your naked eye, it looks like one star. But we're going to go ahead and slew over, and I'm going to stop to share and we'll go back to live view, Richard.
yeah.
And we're going to slew on over and see what Castor really is. And what you're about to see here.
Oh yeah, there we go.
Yeah, let me get. Oops. Okay, what do you see? Especially look over there on the right hand side. You see two stars there. And if we were to increase the exposure time to a longer exposure, we would actually see a third star. Now, Castor is what we call a multiple star system. It's actually six stars.
Huh.
There's two stars that you see pretty prominently right here. Castor A, which is the bright bluish one, kind of on the lower right, and then Castor B, which is the a little bit more yellowish one on the left. If we were to do a long exposure, we would see a third star very close to these, a little farther apart. That's called Castor C. And so, to at first blush, especially if you do a longer exposure, it looks like you see three stars there. But it turns out all three of those stars are what we call spectroscopic binary stars. They are actually two stars, orbiting around each other so close together that even in the telescope, they appear to be one star. So the two stars that you see in this image here are actually four stars. And then if we were to do a long exposure, we would see a third star separated a little bit farther away. And that third star is also a spectroscopic binary. So the Castor system, which looks like one star to the naked eye, is actually six stars. And this is not unusual. It's very common for stars when they form in those clouds of gas and dust to form as binary systems or trinary systems or even multiple star systems. Now, Castor A and B orbit around each other, and then they have a very faint companion that orbits around each of them. And then Castor C orbits around both Castor A and B. And Castor C actually takes quite a while to orbit. I think it's like 1,000 years or something like that to orbit around A and B. So this is pretty interesting.
It's
And,
really remarkable that they've managed to settle into a stable orbit with that
right,
much
right.
gravitational pull coming from all of the members of this system. You
And
know, the three body problem is supposed to be really complicated. This is six.
yeah, yeah. I was looking at a diagram the other day where they were trying to diagram what the orbits look like, and it was very confusing just looking at the diagram because, they were trying to show the fact when you have two stars that are so close together that even in a telescope you can't distinguish them as two stars. They orbit each other very rapidly, and neither star is stationary relative to the other one. They actually orbit each other uh, as kind of like a seesaw or something like that. Um, so they're wobbling back and forth as they orbit. That's one of the clues that we have that there is another star orbiting each of these two stars is the fact that the stars wobble back and forth. And then if we look at them spectroscopically and watch the spectra of the stars, we don't see one spectrum, we see two. And the
I want to
two
point
are
out that
shifting back and forth to each other.
Gerald, I want to point out that answers one of the questions. There was a question about what would be the minimum size telescope to be able to separate the Castor stars. These two are pretty easy to see, but the spectroscopic binaries you
Yeah,
can't really see. It's an
yeah,
instrumental type thing that we use
right. Yeah,
to
you
determine
can't,
that.
you would not be able to see with any telescope that there's actually four stars here. What you would see is the two stars, but when you do it with a spectroscope, you see two spectra instead of one, and the two spectra are shifting back and forth relative to each other.
And that's instrumentation added to a large telescope,
Right,
not making a very large telescope.
right.
Uh,
Uh, so this is actually quite common. A lot of the stars that you see with your naked eye as a single star, when we look at them with telescopes, we see that there are two stars or three stars or four stars, and in this case, six stars, all so close together that to the naked eye they look like one star. Quite common. In fact,
Yep.
I've heard,
Over, I believe over 50%, or is
yeah,
it?
yeah, I was just going to
Yeah.
say that. Yeah, yeah. All right. Okay. What else would we
Yeah.
like to look at?
Well,
You want to try
we
for
could.
M1 or
I was thinking M1 is probably a great idea while it's
okay.
up, and I don't know what kind of result we'll get, but I'd be really interested to see.
Well, let's head on over there.
Yeah.
It's in a different part of the sky, so I'm going to do a little
Yeah.
hop, skip, and a jump here. I'm going to go over to
Yeah, we should probably sync midway.
yeah. I'm going to go back to Aldebaran. We'll
Yep.
sync on that.
Yep. So M1 is a supernova remnant. So
Yeah,
it's a
it's
different type of nebula. Again, a huge cloud of gas that presents itself in some very complex shapes, illuminated by a massive amount of radiation that still remains in the remnant of the star that went supernova, which is now a neutron star and also what's called a pulsar. So the neutron star is spinning at a predictable rate, and every time it spins, it sends out a pulse of energy that we can detect here on Earth. So if you point a radio telescope at M1, or otherwise known as the Crab Nebula, you will hear that pulse, and you're able to know then how fast that star or star remnant is spinning.
Can you back off on the Zoom,
Oh
Richard?
yeah, hold on. Yeah, it's 205%. There we go. Let's put the bullseye on there so
All
you can
right.
get close.
Okay.
While you're working on that, we have an unrelated question. This goes back to the comet that hit Jupiter back in 1994.
Yeah.
Ah,
Are there any
Shoemaker
traces of
leaving.
that still visible?
Schumacher Levy. Yeah,
Right.
Shoemaker leaving
Schumacher
behind.
Levy.
The
No, no,
question is
no remnants.
right.
No damage. It buffed right out.
Right. Because Jupiter is a gas giant, it
Yeah.
just kind of fell into the gas and it all got evened out again.
Over time, there
Yeah.
was.
There was visible for a while.
Oh
Sure.
yeah. No,
And that was quite a shock.
it was
How much
amazing.
so?
Yeah, those black patches it left in the atmosphere.
Okay.
Okay, so that's Aldebaran.
That's Aldebaran, right?
Yeah.
Now I'm going to go to M1.
Okay.
M1 is a huge nebula. It's the remnant of that supernova explosion that I was telling you about, the one that happened in July of 1054.
Hmm.
Don't pick up your binoculars and try to see this one.
And
Yeah.
Gerald, I thought you were going to say, and I remember it well.
I didn't want to make anybody feel bad. Okay, so you're going to have to do a long exposure on this.
Yeah, I'm going to do, what do you think, 40 seconds maybe?
Yeah, maybe something like that. Yeah.
Let's try that. Okay. We'll
So
admire.
again, this
We're still admiring our clown face there, and
Yeah.
we have to wait for the other exposure to complete itself before we see it.
So this was a supernova that was seen from the Earth in the year 1054. I think I read somewhere it was actually July 4th of 1054. And again, it was seen in the daytime, so it was pretty bright. Now, there's some debate about when Betelgeuse goes supernova, whether we're going to see it in the daytime or not. I suspect we will. We won't have to worry about being harmed by it. When a star goes supernova, you don't want to be too close to it because it puts out a tremendous amount of energy.
Okay.
I see something there.
Yeah, it's very dim and fuzzy, as we expect the Crab Nebula to be.
Yeah.
Let's see. I'm going to see if I can bring it out a little bit better. I think we'll take a longer exposure and bump up the ISO also. So you can barely, I'm not going to even try to point it out to folks because it's silly. Let's try going a full minute and try it
What
again.
amazes me is that Charles Messier was able to see this object with his telescope.
Well, I've looked at the Crab Nebula from downtown Oakland through a 4-inch telescope, and I've seen it.
Oh, yeah?
And it's not that hard. And it's just
Are you sure you didn't see a smudge on the front of the telescope?
Yeah.
I wasn't sure at first. It definitely was a thumb-sized smudge, and but the human eye is really, really sensitive, and it's a little harder to get that contrast with the camera.
Yeah.
Also, Messier had darker skies and clearer skies, probably.
Yes, that too.
But
As long as he wasn't
he
right
was-
in the city.
Right.
his telescope wasn't as good. So you'll hear astronomers talking about Messier objects or M objects. This one, for example, is M1. Um, you know the Orion Nebula that we were looking at a while ago. That's M42. And there's a little over 100 of these M objects out there, and the M stands for Messier. Charles Messier was a French astronomer
Okay.
in the 18th century, so 300 plus years ago, and he had this idea that he could make a living
There we go.
by searching the sky for comets. And when he found a comet, he would then approach noblemen, rich people, and offer to name the comet after them for a small fee. That was his plan.
It
And
didn't work out too well.
it
There
didn't.
are outfits who claim to be able to do that today. Don't send them any money.
Oh yeah, yeah.
Yeah, yeah,
Don't buy a
Yeah.
star.
yeah.
All
So
right.
anyway, he
Yeah.
did this, and his method for doing this was to scan the skies, look for faint little fuzzy patches, and then watch those fuzzy patches over a period of a couple of days to see if they moved. If they moved, then likely it was a comet, and voila, he'd go out and find somebody to pay him to name it. Um, but what he found instead was a lot of faint, fuzzy objects that didn't move. And rather than having to sort of rediscover them over and over again, he finally got smart and made a list of all these faint, fuzzy objects. And it ended up having, I think the original list was like 104 objects or something like that. And that way, when he spotted something, he would check the coordinates real fast and say, "Oh, this is M15 because I've seen it before," and so then he'd move on. To our knowledge, there are no comets that were actually discovered or named by Charles Messier, but his catalog of non-cometary objects is still in use today. So this is number one in his catalog.
I think he did get credit for one or two comments. I'm
Oh yeah,
not absolutely sure on that, but it seems to me someone told me that. We'll have to look that one up.
he probably found more, but we don't know about him because he named them after some
All
nobleman.
right.
Well, so anyway, it's not, this isn't going to be an award-winning photograph, but at least we're able to create enough contrast and stretch it enough that you could actually see that there's something there. And this nebula, it's pretty big. I mean, it goes out to about here on the right, all the way to about here on the left. However, while you're admiring that white smudge, oh, and the center of it is right about there. I am going to be
Now
looking.
Conrad Jung actually took a picture of this object with Nellie, our 36-inch
Ah,
telescope,
great.
but he did like I think 20 or 30 minutes of exposure time, and I just happen to have that
Oh, that's
image.
great.
So let me just
Because
share
I
that.
was I was sitting there searching for another image of it, and you happen to have one
I happen to have one
on hand.
right here. There you go. So
Yeah,
this
that's a
this
lot
is
better.
this is taken with our telescope, the same telescope, and you notice the angles are about the same. So this orientation compared to the image you had, Richard, is pretty much the same. Here's that
Yep.
dark region that you were talking about, and here's the central part right here.
Hmm.
And you can just see that this is a chaotic spray of gas and dust blown out by this star when it exploded in a supernova explosion. And
Well, this is a great example of how spending time on an astrophotograph makes all the difference.
right,
You know
right,
what I'm doing here with the camera when we go live is like the vacation snapshots of
Yeah.
astrophotography.
The
But
quick and dirty.
yeah,
it's
Conrad spent hours taking images and then stacking them and processing them and getting the signal to noise ratio at the right place and bringing out the contrast and adjusting the color uh, curves and all that all that fancy stuff that we have to do to process astrophotographs after the data is collected. Whereas what we're doing when we do these live programs is cross our fingers, knock on wood, and take an exposure and hope we have something to show you. It's a whole different approach.
Someone asked how far away M1 is, and
Uh,
I don't remember off the top of my
Here, I'll
head.
look. John, you want to look that up? Yeah, it's
I am
probably
in the
easier for
process
you.
of looking that up. I saw the question. Hang on a second.
Great.
All right. And so, people have kind of been conditioned to think that this is how most stars die, and that's not the case. Most stars die as planetary nebula, the very slow process of, the star swells up and then it loses its outer layers of gas over tens of thousands of years, and then it collapses into a white dwarf and it's surrounded by a shell of gas that looks nice and pretty and is very symmetrical and so on. Supernovae only happen to actually fewer than 10% of stars, and they're the really massive stars, stars that have 8 or 10 or 15 times the mass of our sun. Those are the stars that end their lives as supernova explosions. Now, if they're just a little bit more than 8 times the mass of the sun, the star remnant collapses and becomes a neutron star. Um, if they're really massive, like maybe 20 times the mass of the sun, they collapse all the way down and become a black hole. So this one is a neutron star, and they emit a lot of radiation, a lot of gamma radiation, neutrinos. If we had a really good neutrino detector, uh, one way we would know that there had been a supernova somewhere nearby or even far away was the sudden increase in neutrinos that we would detect. Uh, so, pretty dramatic event, but actually quite rare. I read somewhere that there is a supernova in any one galaxy about once every 100 years or so. Fortunately, there are a lot of galaxies out there, so we see them pretty routinely happening in other galaxies. And when they happen in another galaxy for a brief period, of a few days, it's so bright it actually outshines the combined light of the rest of the galaxy. So it can be pretty dramatic event.
So the distance is about 6,300 light years.
All right.
Oh, great. Thank you, John.
Sure.
I'm glad I didn't give my answer. It would have been totally wrong.
Okay, we're kind of coming up. We're a little after 10 o'clock now.
Yeah.
So I guess we can kind of wind things down. Once again, I want to remind everybody if you can click on that donation button on Facebook or go to the Chabot website, chabotspace.org, and make a donation. You would really be helping us out with our virtual programming, also with our development of new exhibits and programs. So when we reopen the Chabot Space and Science Center after the pandemic is over, hopefully sometime middle of this year, uh, we'll be able to hit the ground running, and your help will be greatly appreciated. So hit the old donate button, please. All right.
All right. Well, I guess that's it. Good night, everyone,
All
and
right.
hopefully we'll have a good clear sky next week as well, and we'll be able to do this again.
Yeah. So have a good evening.
All right. Take
All
care,
right.
all.